we reduced the problem of calculating this transverse susceptibility to solving the self-consistent equation for the vertex. We managed to do this. What again appeared is an expression for the vertex in terms of like a fraction where in the denominator appeared the polarization operator. So this was actually an exercise to do, but let's just repeat some steps in the calculation of this polarization operator that we need to have to see what is going on in the system in terms of spin correlations. So what we have to evaluate is again the polarization operator, and now to do this, well, in the first step, it's actually an exercise. One can do the Matsubara summation here, just for a generic system. So if you do this, you should get, now here's the sum over then the d-dimensional space, and there's appearing from distribution functions. Let's call this C. And what I introduced here, like what we had introduced before, was the energy measured from the chemical potential, this is psi. Okay? So this was actually an exercise for, I don't know if you already did it, for the Matsubara summations. Okay, so this is just looking at the Green's function, which have simple poles. If you do the technique that we learned how to do, you will see that the Fermi distribution functions appear here, because what you do is you express the Matsubara summations in terms of a contour integral, where you multiply the integrand by the Fermi distribution function. Okay. So this is up to here independent of details of the system, but now to do the final sum, one should specify the system. So let us now specify the dispersion and dimensions. So now concentrate on isotropic 3D system with dispersion epsilon p squared over 2m, and at temperature 0, okay? Going to 0 temperature. And then to do the calculation, well, we can talk about what is the momentum q that appears here. And what we said is, well, this q is the momentum that defines the vertex, and it will be the same that defines the transverse susceptibility, okay? Because in the transverse susceptibility, the q, was just a Fourier transform of the distance between the spins that we look at and the time. And this external momentum was always fixed. This also appeared as an external momentum in the vertex and so on, okay? So now, to simplify our lives, let's think what we're interested in. We said, well, let's see if magnetically something interesting is appearing. So we said, let's look at separate points in space and see if we flip here an electron spin of the itinerance of freely moving electrons, flip a spin and see what happens at a far distant point sometime later. So what we're interested in for this response actually should be like far distant points. But far distance points means then that, well, if the distance is large, that the momentum q is small. So we look at somehow long wavelength correlations, okay? Which means we can look at the limit q going to 0. And then we said, well, let's look at the case that we flip it here at some time 0 and then at the response at some time t. So we can even look at the case where we, let's say, integrate over the time tau. Okay, so whenever the response, whenever it wants to happen, can happen. So this would correspond to the case of taking the Matsubara frequency omega into 0. Okay, this just simplifies our life. And what we just want to have is an insight into what is magnetically going on. Now, of course, we don't want to look at local correlations, which would mean we have to keep high Q to resolve small scales, but we're interested in long scales, like what is appearing far apart. This is nice for us because we can concentrate on small Q, and then the response we don't care, like if it's instantaneously or long time, so we can look at the static limit of this correlation function. Okay? This we can keep in mind. And then do the following simplifications. So the P here, again, is the P of the free electrons. This is always like stick to the Fermi surface, and you can see this immediately again here in this expression. So we have a difference of two Fermi distribution functions which differ dispersion at P and P plus Q. Q is small. So the Fermi distribution function is a step function in the zero temperature limit. So for this to be finite, the P has to be at the Fermi level. Because only then you can have here, let's say, a 0 and here 1, or here 1 and here 0. Only if this is like really close to the Fermi level, epsilon P can be, let's say, still below. So this is occupied, and epsilon P plus Q is not occupied as well. So the P is close to the Fermi level. So P is Fermi momentum, Q is like the distance. You can always have, like in solid state, P Fermi is of the order of the level spacing, inverse level spacing. So we're interested in correlation functions that are many sides apart, which means that the Q is much smaller than the Fermi wavelength. So we're looking at distance is much larger than the nearest neighbors. Okay? So this you can keep in mind, like saying that Q that we're interested in is much smaller than Q Fermi. And omega m we can think also as in the limit of 0. You can always write omega m. Let's say omega m going to 0. So think in this limit. Then we can use approximations, which are so we'll just write here maybe this once physically. So physically this means correlation function. Correlations between spin or correlation function on long length scales. It's called L, which are much larger than A, the lattice. Okay. You can always have in mind. It's probably not so familiar to you, like this kind of language, like what we're here for. But you understand what I mean, or?
Não tô mesmo. Seria como se você estivesse linearizando essa função?
Eu vou usar para linearizar essas funções, sim, exatamente. Mas a ideia é que você sempre tem essa escala diferente de energias. Você tem o Fermi momentum que é large, mas as funções de correlação que normalmente são long wavelengths. E uma maneira de ver, a gente falou, se tem aqui, let's say, você tem um sistema unidimensional que a gente está interessado em spin correlations. Mas a gente não está interessado em spin correlation between nearest neighbors. Mas a gente quer ver, vamos flipar esse spin aqui, vamos flipar esse aqui e ver se tem uma correlação com esse aqui. Porque isso vai falar se tem correlações magnéticas. Mas isso quer dizer que a distância aqui, vamos chamar de L. E o Fermi momentum tem a ver com 1 over the lattice spacing. Então, se você quer pensar dessa forma, pode pensar o TF é muito large, muito grande, e Q é comparativamente small, pequeno. Então, a gente está interessado nesse limite. Mas se você quer ter outra intuição física, que quer dizer Q muito menor do que TF, você pode simplesmente pensar, a gente está interessado em funções de correlações, em correlações muito mais distantes do que correlações dadas pela length scales, dada pelo Fermi momentum, e 1 over Fermi momentum é uma length scale que seria o lattice spacing. Tá? Então, o Fermi Energy, o momento de Fermi, sempre de certa forma é a escala muito grande para a gente, e toda a ideia de teoria efetivas e essas correlações que a gente está interessado é sempre estudar física numa escala pequena, assim, em longa escala, na verdade, em termos de length, mas em momento de energias muito menor do que essa energia que são energias altas. Okay, so but taking this like as the input, because this is what we're interested in this kind of limit, then we can use now exactly this to linearize.
O potencial químico some ali naquelas.
Tá no psi. Ah, vai desaparecer aqui. Sim, sim, desaparece aí. So using this limit that we're interested in, we can use, we can linearize the difference of the energy. So this is upwards of q squared, which will not be relevant. And then we can also use this to linearize the difference in the Fermi energies. And now the derivative of the Fermi distribution function, well, in the limit t equals 0, this is a step function from 1 to 0. So the derivative will be a delta function minus delta function, which pins the energy to the Fermi energy. Okay, this is just, I mean, saying that, well, for this to be finite in the zero temperature limit, the energy is to be determined. So this can be written as delta epsilon P minus mu, P times Q n. So using this linearization and plugging this in here, you arrive at, so the sign gets inverted due to the delta here, 1 over n, and you have this sum over p, delta epsilon p minus mu, and then you have q over m, q omega m plus pq. Oh, well, okay, so that's the p in the general long wave and like long time limit, okay? But then, like, again, we just want to have an idea what is going on in the system, so let's take a limit that is specifically simple, which would be the static limit of first sending omega m to 0, and then, let's say, keeping q small or finite, or also sending this to 0 in the end if you want. So this would be like the static limit correlations along these space. This limit we can do, just, I mean, we are free to do whatever we want. If you want to just get an insight into the problem, then this here, omega m to 0, then this cancels this, and we are left with this expression here, which is just the definition of the density of states at the Fermi level per size. Okay, so that's density of state at the Fermi surface, Fs like Fermi surface per site. Okay. So that's in an interesting, for us at least, limit, the polarization operator simplifies just to minus, but just to the density of states at the Fermi surface. Okay, actually this was an exercise on the new sheet where one should go also keep now finite omega m and q contributions. So one has then to elaborate on this integral here, not just sending omega m to 0. Okay, so that's was on. Okay, so if we now use this and plug this into our expression for the vortex function, I don't know if I call it plus minus or up down. Probably I call it plus minus. No? So in the limit q to 0, taking a specific limit where we first set omega m to 0, then q to 0. The susceptibility then is minus u p of n, 1 minus u. Okay? So now we have figured out the vertex function, so we can put this into the susceptibility and calculate the transfer susceptibility that we were interested in. Okay? So let's go back to the susceptibility. And let's do this now. We're missing one thing. Okay. Susceptibility, we said we can write diagrammatically in the following way. That's how we introduced the vertex. So we had separated the susceptibility in the non-intacting part, and then the intacting part, all the correlations between the interaction were put in the vertex. So now, let's just do the calculation. I mean, we could now translate all this back into like formulas and then solve for formulas, but we saw like in the previous example sometimes, or actually you can also do the calculation immediately in terms of diagrams. So let's just do the analytic calculation, like bar calculation for the correlation function using the diagrams, and then translate it back in the end, because it's sometimes just seems to be more convenient. So we can write this in the following way. Just factoring out here the polarization operator, and then we can recall what this here was. This was the solution for the vertex, no? Vertex was solved by this, so we can plug this in here. Plus okay, just plugging this expression for the vertex here, so multiplying with the polarization means multiplying here with the two external lines. You get this, so now we can see that we have a 1 minus this, so we can bring this on the same denominator. So we have 1 minus this here plus this here, so this just cancels out. So this gives us a 1 over this here. Okay? And then the 1 is multiplied by this polarization operator, so we get 2 lines here. Okay? Aonde?
Você não podia pegar esse
Aqui?
E botar para fora os dois livros.
Esse aqui não, porque esse está sendo multiplicado aqui. Se eu multiplico esse aqui, isso vai me dar S. E esse multiplicando aqui vai dar S, né? Oi, isso foi a pergunta ou não? Isso foi a pergunta ou?
Não.
Não, então qual foi a pergunta?
E se pegar que esses dois daquele lado, esses não vão multiplicar ali também? Esse termo que você acabou de colocar.
Você quer falar assim?
Não.
Mas aí eu teria aqui demais, né? Porque isso vai multiplicar aqui e de novo multiplicar. Assim.
Ah, tá. Teria que somar.
Certo? Eu poderia também, se você quiser, Ou também poderia ter feito assim. Também poderia ter feito. Tá? Mas, tanto faz. Bom, quem não está sentindo a vontade com isso também pode traduzir em expressões. Só queria uma vez mostrar que é mais fácil fazer diretamente com diagramas. Então, se a gente bota esse, if we put this on the same denominator and then multiply, we just get for the solution. So this would be then the polarization operator, and then we have minus this here. Okay? So if we translate this now back into what we found, so that the polarization operator here would be the density of states. This here is density of states, or actually minus density of states with the interaction line which was minus u. Okay? So if we translate this back, you would get this expression here. Okay, so what happened here still, I mean, if you want to go through the algebra, you can do it. So there was here still a factor minus and then n to the 1 over t. But this is compensated by how we define the correlation function. It also had a factor t over n. So that's why here's the density of state. Okay? I mean, if you feel more comfortable, just translate it back to formulas, but I'm doing kind of like, it's open for your investigation. It's minus things, like conceptually it's like you solve the vertex, and with the vertex you can find the correlation function, how you want to calculate it, just calculate it in a simple way. Okay? But this is now like what we are interested in. So let's thinking, and what did we do? We started out again from the weakly interacting electron gas. However, here now with the screened interaction, we said, okay, some electrons themselves will take for the screening, so let's consider local interaction. So we took a specific model, the Hubbard model, where you have due to Pauli principle only interaction between different kind of spins. And then we said, well, let's look for interesting physics. Physics in the density channel, well, there's something like spin density waves, which has to do with translation, charge density waves, which has to do something with translation invariance breaking. Different story, we can look into this. Let's just think what we did so far in the weakly interacting electron gas. We considered like density channel. We didn't look at processes which could lead to magnetism. So let's look for magnetism. Now, how can we see if magnetically something interesting is going on? Well, let's look at a simple susceptibility, which means let's flip a spin somewhere in the system and see the reaction somewhere else. If there's no magnetic correlation, then this is boring, nothing is happening. But what do we see? We find that the correlation function, so this is like omega m in q going to 0 at t equals 0, actually has something interesting, which is you have here in the denominator the interaction u times the density of states. So there's a lot of information here. So first we see, well, even if interactions are small, what is happening here is there's always appears a combination of density of states with the interaction. So if you have a large density of states, even weak interactions can have a large effect, okay? So that's the one thing. So large density of states can compensate for small interactions, so interesting physics can also be happening at small interaction. Now what we see if we slowly turn on this product here, well, we see that there's building up correlations and something really drastically happens if u becomes, u times u0 becomes 1. Then this is just exploding. So there's a divergency appearing which signals exactly a kind of instability. Okay, so there's an instability appearing, and this is now exactly like what was your question. Well, you're doing again an expansion around the non-interacting reference state. Yeah, we did it because we want to see what is happening, and to see the simplest perturbation theory around the non-interacting reference state. But now we see once u becomes of the order of mu0, or becomes 1 over mu0 becomes equal to 1 over mu0 or larger, then something drastically happened, and we cannot rely anymore on what we did. And this is exactly like the signal that something drastically is happening. Probably our reference state was not the right one, so a divergent susceptibility usually signals the phase transition. Okay? So this is now our insight that, well, this is interesting because it says even if u small, mu0 can compensate for it, and we should understand what is going on here. So there's correlations building up between spins, so probably there's some magnetism building up, so let's try to investigate this now by the effective theory. And what we already see is, well, if this becomes of order 1, there should be some instability signaling that there's a non-trivial mean field appearing for the effective theory, so there should be a non-trivial saddle point signal, then phase transition to some, in this case, magnetic phase. Okay, so that's was the first step, and let me just write down what I just said, some comments here, and then the next lecture we are going to develop then an effective field theory, which again is based on the intuition that we just gained from the diagrammatic analysis. Okay? So it's always the same. Like first you don't know what to do, look at diagrammatics around non-interacting reference state, look at some correlation function, see if something interesting is going on. Here we see, yes, there is something interesting going on, so let's investigate this in terms of an effective theory. So just a few comments. So interaction, constant u appears in combination with the density of states, which means even, i.e. even a weak interaction can lead to sizable effects if the density of states is only large enough. Then physically, what this scaling of this product here with the density of states means is just that this density of states measures the number of final states you can scatter into. Okay, so this is why this appears here. Like you have interaction processes, and the more channels like you can scatter into, well, the larger, the more relevant this interaction process. Okay, so this is just a measure. So mu0 just measures the number of final states. Accessible to scattering process. That's like, I mean, how you know it from Fermi's golden rule or something like this. There are also always pretty density of states. Then, already notice correlations grow with growing u. And something drastic happens at a critical value of u, which is defined by u critical times the density of states being 1. It's a critical interaction. So what actually happens is that at t equals 0, you see mu equals 1, the transfer susceptibility develops a divergency, and this reflects now a quantum phase transition. That's what I mentioned in the beginning. So you have a phase transition at 0 temperature, which here is to some magnetic phase, which we are going to explore more, and which we will see is an itinerant or magnetic phase of freely moving electrons, so a metallic ferromagnetic phase. Okay, so at and above the critical values, okay, I should write down, at mu c and above the Fermi sea of non-interacting electrons, Fermi sea of non-interacting electrons, as a reference state breaks down. As a reference state breaks down. And this is what the diagrammatic analysis signals, that once we are at this transition or at this instability, which is called the Stoner instability, then what actually we should look for in an effective theory, a non-trivial mean field, which takes this into account. Okay? So this is what we're going to do next, like explore the nature of this magnetic transition, but let me just once more comment on this. This is really interesting because this is a transition now that happens at t equals 0 and is driven by an external parameter, like by pressure or whatever you can measure. You can change the density of state and thereby drive this phase transition. So in contrast, like for superconductivity, if you have a small, attractive interaction, will always at t equals 0 have a superconducting state. Okay, but here you have a quantum phase transition tuned by, let's say, pressure or whatever, and of course one can also generalize this here to finite temperatures. Then instead of having the density of states, one would have to calculate the Lintan function. This is just substituting then here by this corresponding susceptibility here instead of the density of states. So you can still express the transfer susceptibility at finite temperatures in simple form, and we will figure out like how the phase diagram is. So that we have some quantum phase transition at 0 temperature, but also have the transition line at finite temperature then. Phase transitions. Okay, let me think if I want to say something more. Just one comment. So what we had before in the non-interacting electron gas, we had in the weakly interacting electron gas, we had this kind of ring structure, no? Which then led to the effective potential and everything. Okay, so this was like decoupling in the charge channel. So now what we have is these kind of ladder diagrams. Okay, where we have here a k plus q and here a k, where the relative momentum between them are small and which is spin resolved. Okay, so the spin up and spin down. So this is what we are going to decouple in the exchange now, then to see what's going on. Not looking at densities more, but okay, we can see how to decouple then the interaction to write and take into account the spin and not the density to be right in effective theory. This is like taking 1 or 2 more lectures to do this then. Okay? Yeah, probably this is the last, provavelmente esse vai ser o último exemplo.